This is an early print of a patent for a hot air engine submitted in 1816 by a Scottish minister, Robert Stirling. After many years of fundamental research in the field of flow and heat transfer phenomena and the introduction of advanced technologies, from this basic idea in the Philips laboratories, a highly efficient engine has been created. But the principles of the original Stirling engine may still be recognized. What then are these principles? At the heart of the engine are the cylinders. In each cylinder, a certain quantity of gas is retained by a piston. Assume that the gas pressure on either side of the piston equals 1 atmosphere. No force on the piston results. With the piston held in position, let the head of the cylinder be heated. The pressure of the gas rises. This force results. Now let the piston be released. It is driven by the expanding gas until the pressure to the left of the piston reverts to 1 atmosphere. If the cylinder head is cooled, the pressure of the gas decreases further. A force is now exerted on the piston in this direction, a force which drives the piston back to its original position. Let us relate this cycle to a PV diagram. We start with this given volume and a pressure of 1 atmosphere. When heat is supplied to the cylinder, the pressure rises. This distance is proportional to the force acting on the piston. When the gas expands, its pressure drops. The force becomes smaller. This area is proportional to the energy delivered by the gas. During the cooling, the pressure of the gas in the head becomes lower than 1 atmosphere. The piston, driven now to the left, absorbs yet more energy. The work done in one cycle is proportional to the area enclosed by the related curves. This cycle turns heat into mechanical energy. But the power of such a device is small and its efficiency low. The power can be increased by raising the pressure on both sides of the piston to a larger value. In the Philips engine, this may be 100 atmosphere or more. The forces induced by heating and cooling will increase correspondingly, as will the energy delivered per cycle. To show this on the PV diagram, the pressure scale has to be condensed. In this case, the cycle starts with a pressure of 100 atmosphere. The area, indicating the energy per cycle, has increased so much that in this new scale the original area can hardly be seen. So far it has been assumed that the pressure to the right of the piston remains constant throughout the cycle. This doesn't apply in practice. The volume to the right of the piston obviously changes. So does the pressure. However, the pressure is kept reasonably constant by including a cavity known as the buffer space. The power of the cycle has been raised. Let us now turn to the efficiency. Not only is the gas alternately heated and cooled, but also the cylinder wall. The heat spent in this way is wasted, but it cannot be neglected as the heat capacity of the cylinder wall is much higher than that of the gas. Robert Stirling solved this problem with the so-called displacer piston. This piston drives the gas from one end of the cylinder to the other, demanding hardly any energy as the pressure on both sides of the piston is almost equal. The cylinder head can now be kept constantly at a high temperature and the other end at a low temperature. The whole cycle can be performed without wasting heat energy on the cylinder wall. First, the gas is displaced to the cylinder head where it is heated. The gas is then expanded and work is done on the power piston. The gas is driven to the right and therefore cooled. And again work is done due to the pressure in the buffer space being momentarily higher. But even here heat is wasted. It is being wasted on the gas itself. A certain amount of heat is supplied to the gas, and yet half a cycle later it is removed and lost. The engine's efficiency could be increased if only this heat could be conserved somewhere to be used later in the cycle. This may be done with a so-called regenerator, a chamber filled with a porous metal which acts like a sponge. During one half of its cycle, the gas gives up heat to this chamber, only to take the heat back on its return. A version has now been developed which enables more than 99% of the heat to be recovered, without offering too much flow resistance. There now remains only one essential reason to supply heat to the cylinder head, and that is to compensate for the tendency of the gas to cool during expansion. Conversely, there is only one reason to remove heat from the other end, which is to compensate for the tendency of the gas to heat up when compressed. Thus, the amount of heat to be supplied and the amount of heat to be removed is reduced to a minimum. The efficiency as well as the power is increased still further by raising the expansion temperature and by using hydrogen or helium as a working gas instead of air. The movement of the displacer piston is regulated by the power piston. A solution outstanding for its simplicity was evolved at Philips. It is known as the rhombic drive. These are the four phases of the cycle. First, the gas is driven to the hot space, where it is expanded, driven back to the cold space, and ultimately compressed. With the use of the rhombic drive, the four phases of the PV diagram will partly overlap, resulting in this shape. The work done is still proportional to the area enclosed. This is how the rhombic drive is built up. The mechanism comprises two pairs of connecting rods of equal length. One pair connected to the yoke of the power piston, and the other pair to the yoke of the displacer piston. The yokes are also of equal length. Due to the symmetrical build-up of the drive, there are no resulting inertia forces in the horizontal direction. Furthermore, the vertical inertia forces acting in the mechanism will not be affected on the assumption that the masses of the pistons are concentrated in their respective yokes. If these masses are equal, then the center of gravity of this rhombus will coincide with the geometrical center. The center of gravity is displaced vertically. The inertia forces which result can be compensated by two identical counterweights, whose combined center of gravity is in counter-movement to the center of gravity of the rhombus. The masses of these counterweights can be evaluated so that the center of gravity of the whole system remains static. This means that this single-cylinder hot gas engine is inherently balanced. Perfect balance means complete absence of vibration at any speed. High speed will lead to high power. Therefore, the engine as a whole has been designed to operate under these conditions. In particular, an improved heat transfer system was developed. This has been achieved by placing more heat exchange units in parallel. Efficient cooling is ensured by subdividing each cooler tube into many smaller ones. All these are embedded in the cooler housing through which water is pumped. The heater is improved by extending the heater tubes, increasing their number, and adding fins. The exact dimensions of the heat transfer system result from a thorough investigation of the Stirling cycle and have been evaluated electronically to minimize the sum of all the losses. In section, it can be seen how a burner is placed on top of the heater. The actual combustor is suitable for a wide range of gaseous and liquid fuels which are fed in at the top. The fuel and air associate to become the hot combustion gases which circulate round the heater tubes. The efficiency is increased by using a preheater. In this, the air is led to the burner against the flow of combustion gases, absorbing heat from them and thus reducing chimney losses. The heating system, being external, is very flexible indeed. It can be adapted to use nuclear, solar, or stored heat energy. This is the end result. The Phillips Stirling engine, highly efficient, powerful, and quietly running. It has turbine properties inasmuch as it can be completely balanced, and for a model with only 4 cylinders, an extremely steady torque is obtained. The Stirling cycle is very versatile. It can also be used as a refrigerator. In this case, there is no need for a heater, and the shape of the head is changed. The direction of rotation remains the same. The machine is driven by an electric motor in what we will call the forward direction. Again, expansion takes place in the head of the cylinder, compression at the base. In the expansion space, the gas will cool. In the compression space, heat does develop, only to be absorbed by cooling water. Thus, heat is transferred from the head to the cooling water. It is even possible to cool the head to such an extent that the air around it is liquefied, as in the case of the famous Phillips Cryogenerator. Thus, the Stirling cycle can be used as the basis for an engine or for a refrigerator, the machine running in the same forward direction in both cases. However, if the direction of rotation is reversed, 2 other modes of operation are obtained. We will demonstrate these 4 modes of operation. When the electric motor is switched on to drive in the forward direction, the machine will act as a refrigerator. The water vapor from the air condenses on the head, and a thin layer of frost is formed upon it. At a later stage, the head becomes so cold that the air itself is liquefied. The rate at which the air is liquefied is best seen by collecting it in a ring. The cold that is stored in the head may be used to obtain mechanical energy. When the electric motor is switched off, the machine itself will start to run, but in the reverse direction. It acts now as a cold gas engine as long as the head remains cold enough. Before the cold gas engine comes to a stop, the electric motor is switched on again to keep the machine running in the reverse direction. Therefore, the head will continue to be heated up, and the machine now operates as a heat pump. We will now extinguish the lights. The glowing head indicates that a temperature of about 700 degrees centigrade has been reached. This heat is turned into mechanical energy by switching off the electric motor. The machine now runs in the forward direction as a Stirling engine. An experimental Phillips Stirling engine has been installed in this floating laboratory. The purpose was to test the behavior of the engine and its auxiliaries in practice. The engine has a rating of 30 horsepower at 1500 revolutions per minute. The working gas is helium. The boat has been provided with an inboard-outboard drive. Let us look at the engine. The large cylinder is the preheater fitted around the head of the engine. The fuel atomizer is seen at the top. The power output of the engine is proportional to the mean working pressure. If the governor is set to a higher speed, helium from a high pressure bottle is blown into the cylinder, quickly increasing the working pressure and the power. The pressure also controls this variomatic drive of the blower that supplies the air required by the burner and keeps the air-fuel ratio constant. On the other hand, by lowering the set speed, a dump valve is opened and a compressor pumps helium back to the pressure bottle. Moreover, a short-circuit valve is opened which makes a connection between the buffer space and the cylinder, thus momentarily cutting the power and giving excellent maneuverability to the boat. Concluding, Phillips Stirling engines provide multi-fuel capability, adaptability to nuclear, solar or stored heat energy, high efficiency, clean exhaust gases, no lubrication oil consumption, and silent operation.